Hello. So this is the next class in the series of elementary particle physics. I mean nuclear and elementary particle physics. So last class we discussed about uh, third component of isospin components. So now we are going to discuss some other conservation law, conservation of hypercharge. Conservation of hypercharge. So it is denoted by generally in textbook Y. What is hypercharge? The hypercharge is defined as the twice of the average charge of the members of group. Hypercharge is conserved for strong and M interaction. This is conserved strong and EM interactions, electromagnetic interaction. Hypercharge is also defined as a twice of difference between the actual charge and the third component of the isospin of the particle. So therefore, this, as I said in definition, it y equal to the twice of difference between actual charge and third component of isospin of the particle. So that is the definition. So the definition I'm going to write like twice of difference between actual charge q and the third component of isospin. Isospin is the I3. Okay. So this isospin is uh, textbooks, different type of forms are there. One is IZ, one is I3, or in some textbooks I observed T3. Okay, you can use whatever you like. So this is I3. So for example, here I'm going to discuss one example. So just one example, uh, a triplet ion. Triplet pion. Okay, so the triplet pion. So we know already I3 component, just we discussed in last class only, right? I3 components are the triplet. What is I3 component? 1, minus 1, 0. These are the triplet components, right? So easily we can get a hypercharge of a triplet component. The charge is 0 and 1, which means y is equal to 6. All the triplet components are there, right? So these triplet components pi plus pi minus pi. So all these components pi plus pi 0, pi minus, all the components the hypercharge is 0. That is the hypercharge. Next, this one is very important in our examination, CSIR GATE examination. That is strangeness number, conservation of strangeness. Conservation of strangeness number. strangeness. Okay. We know hyperons are product. Sorry, these hyperons are produced by some strong interactions, which means almost uh, times that is equal to 10 to the power of minus 3 seconds. 10 to the power of minus 3 seconds. Okay, the hyperons are produced by the strong interactions, and the decay is always by means of weak interaction. So weak interactions, these are the strong interactions, right? Okay, strong interactions, the strong interaction. Okay, so decays are always possible in weak interactions. Weak interactions. So that means 10 to the power of minus 10 second, or team interactions. Team interactions almost 10 to the power of minus 20 seconds approximately. Okay. In this situation, strange particles are produced. Right. Let us show one example here. They going to show you P plus P tends to P plus this ion K plus. Okay. Or else example we can write like this. Another example. So these are the examples of the pi minus plus proton. These pairs, very strong particles are produced. Okay, strong particles. Or else this equation we can go to write this P plus P, P plus, I don't know these are correct or not. I didn't check. Textbook is there. Just I took it from textbook. This I didn't check this one. Their conservation laws are correct or not. P plus P tends to P plus. You can go and check all these examples. Uh, the charge, lepton number, baryon number, hyperon, sorry, isospin number, I3 number, hyperon number. Now, strangeness. Okay. So the strong interaction is involving a new kind of quantum number called strangeness number. So because of this strong number, so it is better to write that sentence. Just one more. The sorry, strong interaction involve a new kind of quantum number called strangeness. Strangeness. It is designed by, so I'll show you here different types of equations. S equal to simplest way, this hyper charge number minus baryon. This is the one formula we already know. So we can go different type of shortcuts. Strangeness number. This is one formula, and that formula is equal to, we know this hyperon price of the charge difference between the I3 component, and B means baryon number, right? These are all the strangeness number formula. You can go whichever you like for shortcuts. So here Y is the hyperon, B is the baryon number, Q is the charge, I3 is the third component, isospin, D is the baryon number. Or well-known formula is there, uh, that Gilman-Nishijima formula. So Gilman, Gilman, Nishijima formula. Okay, famous formula in textbooks. Q equal to I3 plus B plus S divided by 2. Okay, so this is the famous formula. So here I'm going to use this formula frequently, because it's the fundamental form. So we can go whenever some shortcuts are there, right? We can use these shortcuts. Okay. So here the first I'm going to check this strangeness number, the strong particles. Here I'm going to give some hints. How to check these strong particles. The strangeness number indicates that the strong behavior of the particles. So in elementary particles, leptons are there, and I mean bosons are there. The leptons are weak interactions and bosons are strong interactions. Some hadrons, which means K mesons and pi, sigma, cosine, lambda, these are some hadrons are there. So these are exhibit some strong interaction, I mean strong particles. Okay, so group some hadrons, K mesons, these groups, and these quasi group, lambda group, omega group. So these are the groups. Okay. So K plus is there, two groups like that, and K minus, and this antiparticle also there, K mesons, and we know this one. So just wait, I forgot that name. Uh, Here is there only. Yes, in basic elementary particle there. Yes, lambda. So these are all previous classes. If you want these notes, I can send you, no problem. is already there in system. You can send if you want this now. Like just classroom notebook, right? Okay. Just is third group component. This is one component, and this sigma triple components also there. This sigma triple components and this quasi particle. Okay. Oh, minus. These are one group, and these groups also, these complex groups also exhibit this strangeness behavior. Okay. So why I am specifically mentioned here, these are all helpful to solve the problem CSIR NET gate and just omega also. These are one group, and remind these complex values also there. Complex values, complex 0. Okay. These are the particles to behave the uh, strangeness number. First, I'm going to check this k and k plus values. Then we can go one by one. So k plus and k k naught, k plus and k naught. So q equal to what is k plus I3. Formula this one, right? I3 plus variant number plus a strangeness number divided by 2. So this is the simplest step. So first I'm going to checking this k value, this k value, okay, k plus value. So if you try to understand this charge is equal to 1, this one, what is I3 value? I can't remember this I3 value in examination point of and go with the derivation. Simply 1 or 2 minutes it will take place, no problem for me. So 3, I3. What is k plus 2 components, right? I3 k plus 1 divided by 2. 1 divided by, so therefore 1 divided by 2 plus, yeah, this is not baryon, I know, right? So baryon 0 plus I want to find this s value divided by 2. Okay. So therefore uh, it is simple. 1 minus 1 divided by 2 equal to s divided by 2. Then s divided by 2 equal to, so what is this one? 2, 1 divided by 2. So therefore s is equal to 1. Very, very important. If you want to find missing particles, you need to check all this in examination, CSIR examination. They will give one nuclear, I mean, reaction, elementary particle reaction, like this A, B, C, A plus B tends to C plus D. They want to give it a blank number here. We want to find this missing particle. For that, we need to check this all the reaction in this sequence. Charge, lepton number, baryon number, I3 number, sorry, I number, I3 number, Y number, and S number. Then only we can find this missing particle. This is exact question they are giving. So if you want to find this reaction very well, then you are in master in uh, conservation of laws. to finding the this variant and the left hand number. Okay, so try to practice each and every day by using these tricks, then you can easily get the answers. Okay, next thing. Second one, k minus and k minus this antibody. I want to check this k minus. I want to check this one. K minus strangeness number. The formula q equal to I3 plus b plus s divided by 2. So k minus this. I know this hypercharge, just now I check, right? Minus 1 divided by 2 plus this is not variant, which means 0, plus s divided by 2. So therefore s divided by 2 equal to minus 1 plus 1 divided by 2. So therefore s equal to minus 1. Next. So here next I want to go to check this triple component, triple component strangeness number. So in this triple component, I'm going to checking uh, this value. Okay, that equal to. So write down the formula. Q equal to first I3 plus B plus S divided by 2. So this is a simple thing. So for that you need to first find I3. So if you want to find I3, you want to know the isospin values, right? So whenever you want to check these numbers, you need to first find charge, lepton number, baryon number, hyperon number, and isospin I3 component. Then you can arrange this thing. Okay, then you can get correct answer. Okay, this charge is a plus 1, right? So charge is plus 1 equal to what is the I3 component? This component I3 component. How we can check I3 component? M is equal to 2I plus 1, right? How many components are there? 3 is there. I plus 1. Then you can get this minus 1. I equal to 1. All the components are equal to 1. Easy. Like that you can check. Okay. So this is not a. Oh, mm, you need to careful here. So this is variant number. Variance, right? Do you remember variance? Okay. This is variant. That means variant number is 1. This is not a bar is not there. This is normal variant. So this plus 1 charge divided by 2, 0, s plus 1 divided by 2 equal to 0, because 1 minus 1 is there. S plus 1 equal to 0, s equal to minus 1. So therefore strangeness number of triple component sigma plus is 1. So like that you need to check mm, all the components. Remaining components are there. Uh, you need to check this one. Okay, this component. This component, this one is the s equal to minus 2, and n, sorry, this component strangeness number s equal to 1, and this omega minus strangeness component s equal to minus 3. So therefore, whenever you want to find the strong particle strangeness number, so you need to remember this K mesons are 1, K mesons and T particles -1. Uh, this one is the -1, and the sigma triple group is -1. This group, cascade group, okay, group -2 is omega group. Omega not is in group, only single. This is the order. You need to remember this order. So this is how we need to check uh, strangeness number. Sorry, we need to find the strangeness number. So after that, we want to discuss with some applications they identify of the missing particle, okay, by using this charge, lepton number, baryon number, ipron number, I3 component, and the I component, I mean isospin third component, strangeness number. By using this all the conservation numbers, conservation loss number, then we're going to discuss this uh, missing component of the reaction.